Welcome back everyone. In this lecture, we will talk about cyclic groups, and I will try to give various characterization of cyclic groups. So, let's start with the definition. A group G is said to be cyclic if there exists an element X in G such that G is generated by that element. Okay. So, we have seen some examples of cyclic groups. So, let's recall what are those examples. For example, if we take Z plus, it is a cyclic group and it is generated by 1 and minus 1. Okay. So, if we take Z modulo NZ, so then we have seen that this is again generated by 1 plus NZ. Okay. So, we can also take what is called this nth roots of unity. Okay. So, which we denoted by UN. So, this is those X in C such that X power n is identity. Okay. So, this form a group with respect to multiplication, because if X and Y are in UN, you can see that X Y power n will be exactly equal to X power n into Y power n. So, that will be 1. Okay. And the inverse will be there, and so that's enough to say that UN is a group. Okay. It is a subgroup of C star in particularly. So, then you can see that this is actually generated by this what is called primitive nth root of unity. So, e power 2 pi I divided by n. Okay. So, these things you must have seen already. So, now what we are going to say indeed. So, these first two examples, they are very important. So, all cyclic groups must be of this form. Okay. So, what is the meaning of that? For that, so we need to define the notion of isomorphism. Okay. So, basically what we want to say, any cyclic group is either isomorphic to Z plus or Z mod NZ. Okay. So, what is isomorphism? So, isomorphism is that it is like you have defined two algebraic objects, okay, namely groups. So, if you take two groups, whether they are identical or not, so that is what we want to actually see. For example, so let us start with Z and then 2Z. Okay. So, as a group, you are not getting anything new from these two. Na? So, because as a set they are, even though they are different, you can see some similarities are there immediately. For example, I can think of integer as n or 2n, it does not matter. So, whenever I add n and m, you are adding 2n and 2m. Okay. It is the same way you are adding. So, that means this n goes to 2n, it defines a map, and that map preserves group laws. For example, if you call this map is phi, then phi of n plus m is same as 2 times n plus m. So, which is 2n plus 2m. So, which is same as phi of n plus phi of m. And not only that, this phi is easily to see, it is a bijective map. Okay. This phi is bijective map. Okay. So, in this case, we are actually okay to define this Z and 2Z as groups. They are not indeed different, they are same. Okay. So, that is what we call it isomorphism between groups. So, a bijective map satisfying this property, phi of x y equal to phi of x phi of y, is called isomorphism between two groups. So, let me define. So, let us say we have given two groups G and G dash and a map from G to G dash. Okay. And this phi is said to be isomorphism if first condition is phi is bijective and the second condition is phi satisfies or phi preserves the group loss. Phi of xy is same as phi x phi y for all x, y and g. Okay. So, later actually I will go into very much details in discussing this homomorphism between groups and so on. But right now for our purpose it is enough to define what is isomorphism. Okay. So, it is clear that so each element of G can be associated with some element of G dash, and whatever product that you have G is reflected in a similar way in G dash. Okay. That is what this isomorphism actually tells you. So, as groups you do not see any difference between G and G dash. So, they look similar. Okay. For example, Z2 Z, and then you can also see that Z4 Z, they are similar and so on. Okay. So, now what we are going to say, so we write this congruences relation, okay, to say that so they are isomorphic. So, if two groups are said to be isomorphic, if there exists one isomorphism at least between them. Okay. So, now what we are going to prove, so we are going to prove that any cyclic group either isomorphic to Z. So, exactly it is isomorphic to Z if it is infinite group, and if it is finite group and order of that group is capital N, then it is isomorphic to Z modulo NH. So, basically up to isomorphism. So, these are all the only two cyclic groups available. Okay, let us see how to prove this. So, you start with an abstract group G which is cyclic. So, let G, so you assume that it is generated by X be cyclic. Okay. So, now there are two cases, one is order of X is finite and order of X is infinite. Okay. But anyway, once you are given G, then you know that G looks like this. So, the element of G, okay, it is identity X plus or minus 1, X plus or minus 2 and so on. Okay. So, let me write it in both cases. So, this is if order of X is infinite. So, this is the very explicit, when I write it like this, I am saying that these are all distinct elements. So, then this is exactly X power n minus 1 if order of X is finite and you denote it by capital N. So, now what we do, we take these two cases and then define maps. Okay. In the first case, you can see that you can define a map from Z to G, call it phi, and then you send m to X power n. And it is easy to check this map is satisfy this second property of isomorphism, which is called group homomorphism. A map satisfying this property is called group homomorphism. It is easy to see this is a group homomorphism, and since these elements are all distinct, so when order of X is infinite, so this map is indeed bijective map. Okay. So, that means this defines isomorphism. So, now in case 2, you have Z mod n Z and then you have this group G. So, now what you do, you take this I plus n Z and then send it to X power I. Okay. So, now since G has exactly n number of elements, so this map is bijective. Okay. So, the only thing that remains to prove is actually this map indeed homomorphism. So, let us try to prove that. So, let us take two element I plus n Z and J plus n Z from Z mod n Z. So, since we can fix one complete residue class, okay, the representatives. So, we can assume that this I and j, they are coming from 1 to n minus 1. Okay. So, they are integers coming from 1 to n minus 1. So, now if you take phi of I plus n z plus j plus n z, so then you can see that this is exactly equal to phi of I plus j plus n z. Okay. So, then this is exactly equal to x power I plus j. The thing is, we also need to check this map is well defined. Okay. So, that is something easy to check. So, that I will leave it, okay, maybe I will do it here in the side. So, if you, so what can happen, this I plus NZ can be equal to I dash plus NZ for some other I dash. Okay. This is something we have seen already. So, we can choose different representatives for this cosets. So, in particularly if you look at I minus I dash, this has to be some multiple of n. So, in particularly if you raise it power x with that x power I minus I dash, then it is exactly equal to x power k n, then it is identity. So, this would imply that x power I is equal to x power I dash. So, here you can assume without loss of generality I greater than or equal to I dash. Okay. So, this simple calculation says that this map that you have defined from z mod NZ to G, I goes to I plus NZ goes to x power I is actually a well defined map. So, now it is bijective, that is fine, because once you have verified it is well defined, then it is easy to see both have same cardinality, and so and phi is onto, so it is actually bijection. So, now we need to verify it is group homomorphism. For that purpose, if you compute the image of this I plus j, so then you can see this is x power I plus j. So, then this can be written as x power I into x power j. So, then this is nothing but phi of I plus NZ times phi of j plus NZ. It is exactly the similar calculation that you do for integers. Okay. So, that is what you are doing here. So, this proves phi is indeed isomorphism. Okay. So, in particularly what we have proved, we proved that, so we can call this as theorem. So, there are two groups, okay, like two family of groups in some sense of cyclic groups. One is Z plus, that is single element of infinite cyclic group, and all other finite cyclic groups will look like, they look like Z modulo NH. Okay. So, this is indeed helps us to understand the isomorphism classes of cyclic groups. But anyway, it does not say that okay, determining some group is cyclic or not. Okay, that problem is actually somewhat difficult problem. Okay. So, what is the difficult problem? So, even though cyclic groups look somewhat very simple, either they are isomorphic to Z plus or Z modulo NZ, but if some group is given, okay, then if we ask this question when whether it is cyclic or not, okay, so that question is somewhat harder to answer. Okay. We will see some examples later coming from number theory. Okay. But anyway, we will try to understand other properties of these cyclic groups now. Okay. So, now here is one of the important property. So, let us call it proportion. If you take any subgroup, okay, of cyclic group, that must be cyclic. So, we have seen that already for integers. If we take Z plus, so we have seen what are all the subgroups of Z plus. If H is a subgroup, then we have seen that H must be of the form dz, okay, for some d integer. So, but it is easy to that easy to see that dz is again cyclic, it is generated by d. Okay. But this same thing happens for Z modulo NZ as well. So, that is what this proportion says. Any, okay, any subgroup of a cyclic group is cyclic. Okay. So, how do we prove that? Okay. Let us prove it abstractly, so that we do not need to deal with individual cases. So, start with G, assume it is generated by X, okay, and start with H, which is a subgroup. So, H is a subgroup. So, now some powers of x must be there in H. Okay. H could be just identity. In that case, there is nothing to prove. Okay. It is already cyclic. Okay. So, assume that there exists some non-trivial power of x in H. So, there is x power m in H. So, for some m integer which is non-zero. Okay. But the thing is, this m you can assume to be positive, because you by replacing x by x inverse, you can see that it still generates g. Okay. So, this is something I will leave it as exercise. So, if g is generated by x, then definitely x inverse also generates g. So, now by replacing x by x inverse, I can assume m is positive. So, then I can choose d to be the minimum of such m. So, m in n such that x power m is in H. So, I can choose the minimum d such like this. So, then we claim that this H must be generated by this x power d. So, if you think about it, this is what we did even for integers. So, you start with a subgroup H. If it is trivial, then there is nothing to prove. If it is non-trivial, we proved that it will have non-trivial intersection with positive integers. Then you take the smallest positive integer that lies there, and then we proved that actually generates. So, here we are taking that exponential of x instead of that positive integer. So, it is obvious that x power d is in H implies the subgroup generated by this is contained in H. So, there is nothing to see here, but we need to prove the other way. You start with some y in H. So, we need to say that this y must be some power of x power d. So, since y is in G, so that will imply y equal to some x power d dash for some d, for some d dash in integers. So, now you have d and d dash. You want to say that this d dash is multiple of d. Basically, you want to say y is power of x power d. So, in order to say that, you can just simply say d dash is multiple of d. So, now to do that, again we have to go back to the division algorithm, nothing else. You take d dash equal to some k times d plus some r, where r will be smaller than d. Okay. Now, you can actually do the computation. You can see that x power d dash is same as x power d power k times x power r. Now, note that this element is y, is inside H, and this element is inside H, because x power d is inside H. So, any power of x power d is inside H. So, that means if you take this y times the inverse of this element, which is x power r. Okay. So, x power r is y times x power dk inverse. So, this must be in H, because both these elements are in H. So, that says x power r is inside H, but what is the property of r? R is smaller than d, but we have collected d such that it is the minimum among all such positive powers of x, such that x power m is H. So, that forces that r cannot be non-zero. So, that means r must be 0. If r is 0, that implies d dash is multiple of d, that implies y is x power d dash equal to x power d power k, okay, which is in subgroup generated by x power d. So, that proves H is subgroup generated by x power d. Okay. So, indeed, in one stroke we proved any subgroup of a cyclic group, either Z or Z modulo n Z, that will be cyclic. So, this is the abstraction that we need to appreciate. It is the same proof that what we did for Z. Okay. By looking at the abstraction, okay, the things that we used in that proof, that actually helps us to do this proof for any cyclic group. Of course, that means we have done it for z modulo nz for all n in one go, okay, and z as well. Okay. So, we will see what else we can say about the subgroups of cyclic groups. Okay. So, we have already seen something about the infinite group. So, the infinite group is being isomorphic to Z plus. You can see that okay, if order of G is infinite and G is generated by X. So, then you can see that G is isomorphic to Z. Okay. In particularly, given any D integer, you can look at x power D. Okay. So, subgroup generated by x power D. So, that will be a subgroup of G. Okay. So, then x power D subgroup generated by this x power D is there inside G, and this is somewhat isomorphic to D Z. Okay. So, this is somewhat unique association. So, let us recall what we have done in Z. So, Z, if you take, then the subgroups of Z looks like dZ. So, by replacing D by minus D, we can assume D is positive. Okay. So, either D is 0 or D is positive, that we can assume. Okay. So, D greater than or equal to 0. So, then it is not hard to see. So, this association, okay, these are all distinct subgroups of Z. Okay. Because if you take dZ is same as D dash Z and both D dash are greater than or equal to 0. So, then what happens? D divides D dash because D dash is in dZ. So, D dash must be multiple of D, and for the same reason D dash divides D, okay, but both are non-negative. So, that would imply that D must be equal to D dash. So, in particularly the subgroups of Z, they are indexed by dZ and all of them are distinct. Okay. So, this is these are all the subgroups and these are all distinct subgroups of integers. So, that is what you expect to happen even in G. Okay, inside, because it is an infinite group, it is isomorphic to Z. Then I will leave it to you to check for given D non-negative integer, you have a unique subgroup which is generated by x power D. Okay. So, that gives you one-to-one correspondence. So, now what happens if you take finite? Okay, finite actually somewhat becomes more interesting. So, if you take G, which is finite, and assume G is also cyclic. So, maybe we can assume order of x equal to n. Okay. So, then given okay, D which divides n, okay, again you can assume D is non-negative integer. So, D from Z plus such that D divides n. So, that means you can take it to be positive integer, not a problem. Given D positive integer, okay, suppose D divides n, then you can see that you can take this x power n divided by D. Okay. We already seen that the order of x power n by D is nothing but D. Okay. The order of x power D. So, recall what was the order of some power? It is order of x divided by GCD of order of x comma that power. So, here exactly the order of x divided by GCD of order of x comma that power. Since D divides n, so n by D also divides n. So, that tells you that the order of x power n by D must be exactly equal to n divided by n by D, which is D. Okay. So, given any divisor, positive divisor of n, you have a subgroup of order D. Okay. So, now we will claim that this subgroup must be unique. Okay. There exists unique subgroup of order D, and then the uniqueness will come from that it is actually generated by n by d. Okay. So, then we will also conversely we say that these are all the only subgroups. Okay. So, what we proved here, let me just state it. When you have G cyclic and the order of G is infinite, the subgroups of G has 1-to-1 correspondence with the non-negative integers. Okay. The correspondence is given by D goes to x power d, subgroup generated by x power d. So, such correspondence we want to establish for finite group. So, you take a cyclic group which has order n. So, then what we want to say? So, we want to say the subgroups of G. So, G is cyclic, order of G is let us say n, G generated by x. So, this has again 1-to-1 correspondence with those devices which are natural numbers. D divides n. Okay. Where the correspondence is given by D goes to subgroup generated by n by d. Okay. So, now you can see that when D is 1, then it is just x power, when D is 1, then this is x power n. So, the subgroup generated by x power n is just identity. Okay. When D is n, then this corresponds to subgroup generated by x, which is G. So, it is sandwich between identity and G, and then you cover all the subgroups. Okay. So, now we have already established this map. Okay. D goes to x power n by d. So, we are defining the map the other way, and it is well defined, because D equal to D dash will imply the subgroup generated by this x power n by d is same as x power n by d dash. Okay. That is fine, and we need to prove it is actually bijective correspondence. So, we have to prove it is injective as well as surjective. So, let us look at injective. Okay. So, take two subgroups. So, we will start with the subgroup, let us say H is from G such that order of H is D. Okay. So, definitely this H is generated by some x power a. So, we just saw from this earlier theorem that any subgroup of a cyclic group must be cyclic, and we also picked one particular generator. Okay. So, where is that theorem? Yeah. So, we also picked a very particular power of that x such that that x power of that generates this subgroup. Okay. In particularly, the subgroup that we started with, this H, must be generated by some x power, which we call it x power a. Okay. So, now we want to show that this a must be n divided by d. We know that order of x power a is exactly order of x divided by GCD between order of x comma a. Okay. But this is by definition, since order of H is D, so this has to be D. Okay. So, now you can see that so now what you can say about this A. So, this GCD of order of x comma a will become equal to order of x divided by d. Okay. So, now you can see that okay, this x power dA is identity. So, order of x divides dA. So, now if you take divided by the GCD, then okay. So, so order of x. So, it is a similar argument that we did before, GCD of order of x. Now, you can take it to be order of x comma d. So, which will divide a dA divided by GCD order of x comma d. But these two numbers will become relatively prime, that will imply that order of x divided by GCD of order of x comma d divides a. Okay. But already what is given? Given is d already divides order of x. So, that is how we started with, because the d is all those n such that d divides n. So, that means this number is nothing but order of x divided by d. Okay. Okay, that is immediate from here. So, this n by d divides a. Okay. So, now what is a? If you recall, a is the smallest power such that x power a is inside h. So, you already have this okay. So, let us okay. So, let me write it here. So, you have n by d divides a. Okay. So, now if you take this x power n by d subgroup generated by this, since this a is multiple of n by d. So, then this must contain x power a. Okay. So, now you can see that this x power a is contained in this subgroup. So, that forces that this subgroup generated by the x power n by d must contain h. But what is the order of h? Order of h is d. So, this forces that this has order d and this has order d. So, that forces that h must be equal to the subgroup generated by n by d. Okay. So, this proves that if h is another group which has order d, then that must coincide with this. So, that proves that this map is injective. Okay. So, this is injective map. Now, by definition this is onto, because given d you have a subgroup. So, that proves that this is actually a bijective correspondence. Okay. So, this is actually kind of tells you one more information. If you have a natural number d, if that does not divide n, then the subgroup of order d inside G must be the number of subgroups which has order d inside G must be 0. Okay. There are no subgroups. So, basically we have established bijection between these things. Okay. And this kind of classifies all possible subgroups. So, this is something you can apply to Z mod n Z, and then immediately you can see that what will be the corollary. Okay. Suppose if I take Z modulo n Z, okay, for example, take n equal to 4. Okay. And what are all the subgroups? You can see that. So, first of all, the subgroups corresponds to those divisors of 4. So, d equal to 1, 2 and 4 you have subgroup, and if you take this 1 plus NZ, so that is the generator. Then for d equal to 1, okay, for given d you have to take n by d. So, that is the subgroup generated by this. But if you think about it, so if you write it in the exponential notation, you are basically adding this 1 plus NZ n by d times. So, that means the subgroup here is just n by d corresponds to the coset n by d n z. Okay. So, in particularly in this case you have basically 1 plus n z. So, this is one group, and then when it is 2 then it is 2 plus n z, and when it is 4 it is 4 by 4. Okay, this is maybe I should write like this, 4 here, 2 and then 1 plus n z. But 4 plus n z is same as 0 plus n z. So, this is just identity, and this has two elements, 2 plus n z and n z, and this is exactly z modulo 4z. So, these are all the subgroups of z modulo 4z. And for general case, so given d device n, you have exactly the subgroup generated by n by d plus n z will have order d. Okay, so with this I will stop here, and in the next class we will continue with the characterization of cyclic groups, some more properties of cyclic groups.